So today with us, we have David Bruce. He is the Vision Product Manager here at FANUC. David has been at FANUC for 17 years. He's got experience in supporting robot installation. He also spent several years writing application software and has expertise in teach-dependent programming, Carol programming, Visual Basic, and also iRVision programming. Dave's been with material handling since 2009, and we're very lucky to have him because Dave is the source of information on iRVision and vision applications, and I'm very much looking forward to his presentation. So with that said, I'll hand things over to Dave.
Thank you very much, Robert. Okay, jumping right in here. Here's a quick agenda of what I hope to cover in the webinar today. I'm going to do a little bit, cover what Mr. Deckow covered in the very first webinar where he did the iRVision guided pick. So we'll talk a little bit about lighting and imaging fundamentals, just a little bit. Then we'll jump in with the examples that I set up earlier and recorded earlier, and I have some videos we'll go through illustrating the various examples. In specific, we're going to talk about how to do automatic calibration. There's a couple ways you can automatically calibrate an iRVision system. What David showed in the first webinar was I call it manual calibration, where you put the grid down and plot the grid as a user frame. There's ways to do that automatically, so we'll go through that. And then we'll go through a couple different 2D vision processes where we're generating a tool offset rather than a frame offset, which is what we did in the last vision webinar. Okay, iRVision 2D single vision process. So this is kind of the workhorse of iRVision, kind of the main vision process that is used. It's 2D, meaning it provides information in what we call X, Y, and rotation about Z, or called R. It can be used on a fixed or robot-mounted camera, and it provides a fixed frame offset or a tool offset. So the offset is either relative to a specific user frame or to a tool frame, and we're going to be focusing on the tool frame today, how to properly use a tool offset generated in vision. A little bit about imaging and lighting fundamentals. So there's a standard relationship to figure out your field of view. Of course, field of view is important. You want your field of view to only be as big as it needs to be. How big is the feature you're going to be looking at? How much is it going to move around? You know, maybe add 10 or 20% to that. There's an equation here where you can figure out what your field of view is going to be. We do have a spreadsheet, which I've sent out to many people. If you don't have it, feel free to send me an email and I'll happily ship it to you. This is something we've maintained for a while. On it, you can select the various cameras that we support or have supported in the past with previous controller versions. It's pretty basic. You enter your standoff over here. And then for the various focal lengths listed here, you can get your field of view down here. This is in millimeters for your max and min dimension. The ratio is always about 3 to 4 for the field of view. And then there's inches provided down here. And you can add, sometimes I'll add an inch over here for standoff if you needed to know the standoff in inches. Just an Excel spreadsheet. And some people ask, well, what about other lens sizes? You can actually just change this to whatever you want. And through the magic of Excel, everything will calculate for you. So field of view is important. You only want it to be as big as it needs to be. You want to keep into account what type of camera you're using, because different cameras have different size CCDs, and that is that's part of the equation, of course. One thing I'd like to point out as well, this came up the other day, with R30IB, it's always the advanced. People ask that with R30IA 7.7, there was a standard and advanced. The standard was only 640 by 512, as you see here, or 480 by 512. The advanced used the full 640 by 480 in the camera. There's no difference in the camera. It was just the software would cut off about 20% of the pixels. So for R30IB, it's always the advanced. A little about lighting. Lighting, of course, machine vision is 90% lighting. It's all about vision. Of course, works on light. So how you light what you're looking at is going to make a big difference whether or not you're going to be successful. Here's kind of the three broad areas of lighting. There's the dark field where you have the camera, the light source off at a side, the camera overhead. So any scratches or edges are going to reflect right up into the camera. There's the bright field where you have ring light is used, or you have lighting at the same light as the camera, looking down, reflecting back up. Sometimes you get hot spots with that. Sometimes it works well depending on where you're looking at. Really, probably one of the best ways, sometimes a difficult way, but the best way to light a part is by backlighting. It's by putting the light directly underneath. You can turn your aperture way down, and then whatever you're looking at, the part you're looking at is a nice, crisp, dark shadow. Very easy for the vision system to find parts that way and to make measurements, precise measurements and whatnot. So that's a little bit about lighting. Of course, it's all application dependent. We here in the material handling segment, myself, David Deckow, Bernhard Walker, we kind of make up the vision group, and we're at your disposal to help you when it comes to having how you're going to light your application and whatnot. Okay, talk a little bit about the lab setup I have for the videos you're going to be seeing. I'm using, so unlike the previous vision webinar, we don't have our LR made here. We have, I made use of our R2000 IC, the latest R2000 in our lab. I basically made use of it to do all the demonstrations. Here's a setup. I basically just have our trusty friend, the Sony XC56, using a 9mm lens, and we're using 20mm calibration grid. We're about 750mm away. And I'm using the mag switch, an AR50 mag switch, which is a pneumatically actuated rare earth magnet type gripper. We've been using a lot of these for bin picking applications with a lot of success, and it's pretty handy for what I'm doing here. As you can see, that I just put my calibration grid on a piece of steel, and it holds on very nicely when you turn the magnet on. Okay, so now we're going to get into how to automatically calibrate a fixed camera. And a little bit about calibration. Why do we calibrate? Vision system, all vision systems see things in terms of pixels. Of course, the robots work in terms of millimeters. So we need to come up with a mapping from pixels to millimeters. And the way you do that is you provide a series of data points, both pixels and millimeters, corresponding, and then the vision system, the software, will come up with a mapping. So all you need to really do to calibrate vision system is give it a bunch of pixel values and a bunch of corresponding millimeter values, and it'll come up with a transformation for you. And there's a couple different ways to do that, one of them being automatic grid frame set. There's information about all this stuff, by the way, in our manual, specifically the application operator's manual for iRVision. So automatic grid frame set. The steps for that are we select the appropriate calibration grid. So whatever your field of view is, you want to select the appropriate size. You want to attach that grid to the end of arm tooling somehow, and it'd be nice if you could leave it on there permanently. That would be great. Or if you could attach it so that it's in the same place using dowel pins and whatnot, that could be good for when you want to come back and recalibrate later. That could make that quicker if it's in a repeatable position. You want to position the grid within the camera field of view, and then you're going to navigate to automatic grid frame set, which is in the iRVision utilities manual. I have a detailed video here which will show that. Then you go through the steps to do automatic grid frame set. What that does, the output of that is an accurate tool frame for the calibration grid. Then you use that tool frame to then perform a regular grid calibration. So here's in the menu, you go to Vision Utilities, and you go in Automatic Grid Frame Set. Okay, so let's launch our video here. Now I do apologize, there is a cursor on here somewhere. The cursor, you'll see a cursor. This black cursor is the cursor I'm using right now. You'll see the white cursor come up and bounce around to the different screens. So I'm going to try and kind of walk everybody through it. So when I'm referencing a screen, try and follow the black pointer. That's what I'm talking about. The white pointer is what was used previously to navigate through the various vision screens. So what we have up here, down here, this is a webcam video of the robot moving around. We have our iRVision setup, iRVision runtime, and an echo of the teach pendant. So let's just get started here. So first thing we're going to do is go ahead and put our vision calibration grid on our mag tool. So I go ahead, I turn the magnet on, now it's stuck on there, nice and sturdy. And so there goes my the other mouse. Okay, so the first thing you need to do is go to the automatic grid frame set. And here's the interface for the automatic grid frame set. Now notice that it does give you some parameters. You can adjust the R angle limit, the W angle limit. So as you'll see when it goes through the various rotations and positions, you can limit how much it'll need to move in order to calculate the tool frame. These are the default values. Better to use the default values if you can, but depending on how the robot's situated, where it's situated, you may need to lower these so it doesn't crash into anything or get a limit error. So you have that luxury. You can use the automatic grid frame set to discover a user frame. So if you had a fixed calibration grid, you put the camera on the robot, and the camera will dance around the fixed calibration grid and generate a user frame. In this case, we're going to generate a tool frame, and that tool frame is going to be tool frame 5. And of course, that's arbitrary. And we're going to use the camera name. This camera name comes right out of the iRVision camera setup, and you hit choice here, and you would see them all. So we're going to pull up a runtime screen so we can watch what it's doing. When it goes ahead to execute it, you simply hit the execute button. So now I've got the video sped up. When it does, you can exchange your exposure time. You can hit find to make sure that it's finding everything. And then when we're ready to go, make sure no other program is running. So do a quick one from the board. And you can resume or restart. We're going to restart. So now the video is sped up about 8 times, just because it takes about 4 minutes to go through all this. So we didn't want to sit and watch it for 4 minutes. But you can see all the various movements it needs to make in order to come up with an accurate tool frame. Now again, this camera has not been previously calibrated. It's just been set up, focus, aperture adjustment, so it can see what we're looking at. And you go ahead and you run this, and you'll end up with an accurate tool frame when you're all said and done. Okay, so frames updated. So we'll go ahead and just take a quick look at our grid frame. So this is the tool frame for the grid. Now you could alternatively have some kind of pointer over here pointing down somehow, and you could drive the robot up to that pointer and do a 6-point tool frame teaching. You need to do 6-point because you need position and orientation. The orientation has to be correct to the grid in order for you to use it for calibration. So that is an option, but obviously just letting the robot doing it, if you have the real estate, is a much better approach. So now we have our accurate tool frame for our calibration grid. We're going to go ahead and create a regular grid pattern calibration. Call it grid Sony 2 in this case. Go into there. So we're going to select our camera, change our exposure, and put our grid spacing to the appropriate grid spacing. Now we're going to say the camera, the grid is held by the robot, and then we're going to select our tool frame. So what's going on there? So what we did there is we said robot held calibration grid. We said yes. So this flipped from US to UT. So it's asking what's the UTOOL for the grid. And since whatever you do in a calibration, if you can do a 2-plane calibration, that's the best. It's the most accurate. So since the grid is on the robot, it's very easy to move it to 2 planes. We're going to go ahead and do a 2-plane calibration. So it pops up this second plane here as well. So go ahead. Do a snap. So there's our grid. Now also what you can do, I'm creating a little calibration program. That's the other handy thing, is once you have the grid on the tool, you can actually automate your calibration. So you can imagine in your process, if for some reason a camera gets bumped and you need to calibrate it, you can have it completely automated where it goes up, picks up the grid in an accurate location, comes over, runs this little program here to go ahead and perform the calibration automatically. So I'm just going to use this program to kind of hold on to the different steps, the different locations for the 2 snaps. I'm going to go ahead and run to the first point, or record that first point. Now I'm going to go ahead and do a find, so I can set my window sizes to find all the dots. And I'm going to go ahead and watch over here. The robot will move up. I think it was about 100 millimeters. It needs to be at least 25. The more, the better. Okay, so we're going to go ahead. Second snap. You notice the grid got bigger as we moved up. Okay, so we performed the calibration, and we noticed the focal distance came in right. So when you do a 2-plane calibration, it's a perspective calibration, so it'll figure out the focal distance. But we're seeing a high error here. This is way too high of a maximum error. So we're going to figure out what's going on there. We'll go to the points. So here's all the calibration points, the data, and so there is. You click on the arrow, it'll sort, highest or lowest. So so what happened here is there's enough of a shadow there that it thought there was a circle there, and of course there isn't a circle. So when it runs back through to check the calibration, you get this large error. So what you can do is you can actually delete that. So we're just going to go ahead and delete. So you just delete that data from the calibration, refigures out the transformation. Now there's still another point somewhere in the second plane, or the first plane, because again there's 2 separate planes, 2 separate sets of data. So here's the same thing happened when we were lower on the first plane. So we're going to get rid of that point. And now our calibration, oops, sorry, let me go back there. So now our calibration is better. So it was under 1. We'll go back to that in a second. So what happened there? So you deleted the bad points, but the issue is when you try to do the automatic calibration, you're going to get that error again. So really, the true way to overcome this is to fix the problem, either clean the grid, or in this case, what I did is I went ahead and I increased the exposure so that those shadows wouldn't be found as circles. So now that I did that, go ahead and recalibrate. So now we can see that the mean and the max error are significantly lower. So this is a valid calibration now. So we'll get out of there, and then we'll go ahead and we'll run our little program just to show you how it works. So you can run this now. Now that you've got your window set, your exposure set, you can go ahead and automatically recalibrate, provided the UTOOL for your calibration is valid. So that's the first step. So that's how you would do an automatic calibration using automatic grid frame set. Now we'll talk about the other option for automatic calibration, robot-generated grid cal. So the steps for robot-generated grid cal is you don't need a grid for robot-generated grid cal. All you need is a nice target, a nice GPM. And then what's going to happen is the robot is going to detect it's going to discover where that GPM is relative to the faceplate, come up with a UTOOL, and then the robot's going to go ahead and build its own grid, basically. So you position, so you select an appropriate high contrast target. The center L from the vision grid actually works well, and that's what I'm going to use in my example. But it doesn't need to be a calibration grid. You attach that target to the end of arm tooling. You position the target in the camera field of view. You create a special calibration. There's a special calibration for robot-generated grid cal. So you go ahead and create one of those in iRVision. You navigate, then you navigate to the utilities menu, and you perform the 3 steps of robot-generated grid cal. Those being the target calculation, the program generation, and then the output of the program generation is a TP program, which you then run, which then actually does the calibration. So similarly, you go to Vision Utilities, and then you go to robot-generated grid cal. And let's get into that here. So first thing we're going to do is generate a special robot-generated grid cal. So we're going to go in there. We're going to select our camera. So you can see, I'm going to go ahead and put my target on. You watch over here. It's going to use my grid. It's a nice high contrast target, easy to train, easy to see. There it is. Turn my exposure down a little bit. So now you get a GPM with robot-generated grid cal. So I'm just going to go ahead and train the center L as my calibration. Do a quick snap and find. You notice the degrees of freedom. These are preloaded. The values are going to need to be, because it's going to dance this thing around similar to the grid frame set. So it preloads these with some values. Sometimes as it's going through the couple of steps, it may not be able to find it, so you may need to come and adjust these and restart, which you can do. Make it a little bigger there. Just cutting off that one circle. Not really a big deal, but I don't know. Just usually I like to just use the L. I'm going to get rid of these two dots. Could leave those in, really. Doesn't really matter. So there we go. I'm going to change my overlap down to 5%. That'll prevent it from finding it flipped with a ghost circle, which sometimes it'll do. So we'll go ahead. We'll record our start point. Set our plane spacing to 100. Again, I think it needs to be at least 25 or plane. The default is 100. And there's your start. And you notice your start point is recorded. It's a joint position, so you don't. If the tool frames are changing on you, it won't matter. It'll just go back. It'll move to this position using a joint position rather than a linear position. So we're done with that. We get out of that. So we set up our robot-generated grid cal. Now we come over to our Vision Utilities menu, and we go into robot-generated grid cal, and we're going to select the one we just selected. And there's our uninitialized target position. So in here's a setup. So you can record your start position here or in the iRVision. You can select your camera here or in iRVision. Your plane spacing. And then what UTOOL? So what it's going to do is it's going to generate a UTOOL for the target, and it's going to plug that into UTOOL 9, and you can change that if you don't want to use 9. And then this is how big a grid it's going to build. It's going to build a 7x7 grid, and it's going to do 2 of those. And that'll make sense when we're all done. And then the program name that you actually run to do the calibration is by default the same as the calibration, but you could change that through this menu. So we're going to go ahead. So now we're going to do the first step, which is target calculation. We're going to shift run. And again, I've sped this up about 8 times. So here you do get some feedback on what it's done, how many steps, where it's at in the process of calculating the target. So once it's done all its motion, it takes about 3 to 4 minutes. So there we go, that's done. So it's calculated a UTOOL. Now it's going to do program generation. So the first thing it does is it verifies that the target is correct. And now it's discovering the limits of the field of view so that it can generate a program to move the robot through. And you notice it just came up, and now it's going to discover the limits of the field of view on the second plane, 100 millimeters up relative to the first plane. Okay, so again, those 2 things take each about 3-4 minutes. So here's our tool frame, and if you navigate to tool frame 9, you'll see that the values it's calculated have been automatically plugged in. Excuse me, to tool frame 9. So now we did our 2 steps. We calculated our tool frame for our pattern, and we generated a program. So now we're going to run. We're going to navigate to that TP program. It'll be in our select list. Excuse me. And there it is there. So this is the TP program. We'll talk about this in a second. And actually, you can generate this program offline. You don't need to use program generation. You can actually, all the instructions you see in here, you have access to through iRVision. So you could generate this program entirely offline if you already knew an accurate location for your pattern, let's say. So we're going to go ahead and run that again at 8 times speed, and you'll see the robot go through and build its grid. So see, as you can see here, it's just iterating through a 7x7 matrix that it calculated in program generation, and you're just getting exactly what you get with a grid. You're getting a series of pixel values and millimeter values, so that it can you're generating a data set that it can then use to generate a calibration. So there we go. Once it's complete, you see on the runtime screen all the data, and if you can then navigate in, and you can go ahead and see our focal distance is good. It's a 9mm lens, and as you focus it, it's going to, the actual true focal distance is going to change a little bit. Our errors are nice and small. Okay. Okay. Now, okay, so let's spend some time looking at that program that it generated. So this is the program that was automatically generated. This is the beginning of the program. This is the end. So as you can imagine, you could not only could you generate this program from scratch, but you can actually make changes to it if need be. So you imagine if you had quite a large field of view, which is when you want to use robot-generated grid cal, and there was something in the way of this generated program, as it was moving from this corner to the next, you could actually delete a point. You don't need to have all 49 points in there. Or you could change orientation of a point, move it up, move it down. It doesn't really matter, because when it executes this, it finds the pattern, and it knows where the robot is because it has an accurate UTOOL, so it ends up with a valid data point. Not all the plane points need to be on the exact same plane, because it knows the Z as well, because it knows the tool frame for the part. Now it does this. It was kind of hard to see in the little video, but it does this iRV backlash move. And what this does is it moves all the joints 1 degree one way and then back. And that's just to take the backlash out of all the positions, try and make it as accurate as a position as possible before it goes ahead and finds that part. So again, you can generate these instructions are available from the iRVision menu within TP, within programming TP. And then you just give it a request for each of the plane starting at 1,000, and then for the second plane you start at 2,000. So and then when you're done, you send it a request of 2, and it goes ahead and it takes all that data and generates a calibration for you. Another thing to notice is that all those points that it generated, they're all joint representation. So if you do change your UTOOL a little bit, it's not going to wildly change the points. Okay, so there's a couple different ways you can calibrate a camera to use for a tool offset, or you can calibrate a fixed mounted camera. That's a couple different ways you can automatically calibrate a fixed camera. Now we're going to look at using those calibrations to generate a tool offset. The first one we're going to do is we're going to test it using the calibration grid. So we're going to use our calibration grid here, and we're going to go ahead and we're going to just teach a pattern to it. Again, using our center L because it's a nice target. And the key thing to remember is when you're doing a tool offset is that all the positional information is relative to the tool frame, not the application user frame. And there's a little screenshot from our 4D display, which is very handy with iRVision. If we get a chance toward the end, I'll pull it up and show you. But just a side note on 4D, when you have 4D enabled and you have a vision system, it'll show you once the camera is calibrated where that camera is. Again, this would be live. This would be actually on the teach pendant, and it'll show you the tool frame, the triad for the tool frame. The key thing to remember is that if you're going to generate a tool offset, you need the z-axis of the tool frame you're using to be parallel to the optical axis of the camera, or pointing up into the camera, or pointing away. Either way is fine, but it just needs to be parallel to the optical axis of the camera. So let's get into our video here. We're going to go ahead and create a vision, just a regular 2D single vision process. TESTGRID. We go in there, so it's brand new. We go ahead and use one of the calibrations. I'm not sure if that was automatic, grid frame set or robot generated, doesn't matter. They're both valid. We're going to train our pattern. What we're going to do is we're going to make our pattern the L, and I'm going to, just to make it easier to look at, I'm going to change my origin to the exact origin of the grid. So this is actually where our tool frame is. It doesn't need to be exactly where your tool frame is when you're doing this, but this happens to be where it is. So I'm just going to go ahead and drag my origin down here. When you create a GPM in iRVision, it gives you a position of that GPM, but that position is actually relative to the origin of the GPM. And that origin is by default the center of that box you initially draw, but you can move it after the fact. And that's what I'm going to do here. I'm going to drag it over there. So now, and I did that by hitting the set origin. There's also a center origin. If you have a symmetrical pattern, it'll automatically center it for you. So now we're going to go ahead and we're going to go from fixed frame to tool. We're going to tell it what tool. We're going to use UTOOL 5, which was calculated for us through automatic grid frame set. And then we're going to do a snap and find. So this information is relative to the tool frame, and it kind of makes sense. X is pretty close to 0 because I moved my origin right very close to 0. The calibration is a perspective calibration, so you can change the part Z height, meaning it's a perspective calibration, so it knows the correct millimeter per pixel spacing at different levels, but you have to tell it what that level is. It needs to know the distance from the camera to the feature, and it gets that information by you telling it the Z height information relative to the tool frame. So I'm just going to go ahead and change, just arbitrarily change it just to show you that these values do change. Now they didn't change very much because it was a pretty small change, only 25 millimeters. We'll go ahead and, so now we're at 0.15, negative 0.2. We'll go ahead and make that minus 100, just a bigger change, and you'll see it changed by about 2.2 millimeters, which again is not much. Again, we're about a 700 millimeter spacing, so 100 millimeters is not a huge change versus the standoff. But the point is that it's important that you have accurate, accurate information as to where the feature is relative to the tool frame, and you need to tell it to the vision system. For our application, it's going to be 0 because it is right at the tool frame, which just makes it a little easier. Okay, so we'll put it back to 0, and we'll go ahead and we will turn on our crosshairs. So we're going to turn on the crosshairs so we can kind of see this is exactly where this is going to be our reference position. The reference position of the grid is going to be right in the center of the of our field of view. So just a nice easy way to confirm when we move it back there. I'm going to set my reference position. So there's my reference position. So now my vision process is set up. I'm going to get out of there, come over to my teach pendant, and go to my program. Just test TO. So here's my very simple program. I'm going to go ahead and change my vision instructions to the process I just created. Just TESTGRID. So my run find and get offset, going to use VR1. So now that we haven't changed anything, so we run our vision, we're going to see what our offset is, which should be 0, because this is our reference position. So we'll go ahead, here's our runtime screen up now. So there we can see, here's our vision register. We could see that the offset is 0, the found position is what it was, 0.1, 0.2, and then the angle was 86, that was just the absolute angle of the pattern. But our offset, you can see, is 0, which you would expect because it's at the reference position. So I have a little motion here which would actually apply that tool offset to correct for any change in the position of the grid relative to the tool. Now notice I'm just using a V offset VR1. With V offsets, it has a type field, so it knows that it's a frame offset or a tool offset, and it'll apply it correctly to the motion. So I'm going to go now, I'm going to walk in and test it out. Here's where the magic happens. I'm going to go ahead and randomly move the grid to some new position. Now I'm going to rerun my program. And so we can see here our grid is moved. And we have to execute the get offset. Okay. So our grid's moved. Here's my new found position, and here's my offset. So this is my tool offset that I'm going to apply to reposition the grid back where I want it, back to its nominal position. There we go. So I just executed that little bit of motion. So when we come back into here, you'll notice the tool, the grid is exactly aligned with the crosshairs, or the center is aligned with the crosshairs. You'll notice that the tool, when I do a snap here, the tool is going to be in a different position. So I'll come back over here, do a snap and find. So you can see here my robot has actually moved a very precise amount to put the grid back where we wanted it, where it started. So we've just tested out our calibration and our tool offset vision process. And notice too that now our XY values are always relative to the tool frame. So even though it's back where it was relative to the camera, the data always comes back relative to the tool frame. The relationship between the part and the tool frame is different. And we're using tool offset, the absolute information is always relative to that, even when you move the robot around. So as I move it around here, you'll see that the data is really staying exactly that same 10 and 18. So that's what it is relative to the tool offset, the tool frame, which now is somewhere over here, I believe. It hasn't moved, but the part has moved relative to the tool offset. So that's kind of a quick and dirty way. And that's one of the things I always like to do when I'm setting up an iRVision system is kind of just set up some simple tests and make sure it's doing what I expect it to do. That way you know it's been set up correctly. Here's that TP program I use, very simple. View position, you got to use the UTOOL that you're using for all your motions. Just move to my view position, run my vision, get my offset, and then just to test it out, I go ahead and I apply that right back to that same position to get the part back to where I want it. And this is just an arbitrary point, and in this case I was using U frame 0. It doesn't really matter what your user frame is in this case. Your tool frame does matter. Okay, so now we're going to go and try and move on to a real process, what I call a blind pick application. What we're going to do here is we have this bar, and imagine there's an application where maybe these are coming down on a conveyor, or maybe an operator's loading this cable, and the robot knows where it is in one dimension, but not in the long dimension. So it's going to pick it blindly, and then it's going to discover the end, and then it's going to load it back to the table in the proper manner. So we're going to pick it up, bring it over to our camera, teach a pattern for the end, and then we're going to drive it back to the table and use that tool offset to make sure that our bar is aligned with the end of the table. Let's jump into that here. So here's our test pick program, and we'll go over that when we're all done this. So we're going to go ahead. We got the part set up in the nominal position, which is important. We want it to be, this is where we always want to come back to. So we have our part where it's supposed to end up. We come over, we pick it up, and we bring it over to our camera, to our view position. And now we're going to create a new process. call it bar 3. We're going to go in there. We're going to make use of one of the calibrations I did previously for the camera. We're going to teach our pattern. Mask out some of the unwanted edges we don't want, like the seam in the carpet beneath everything. Don't want that. And the 2 center lines I decided I didn't need as well, so I'm going to mask those out. And then what I do here is I use an emphasis area. Since there's not much information, there's a big edge here and a big edge here, not a very big edge here. So this edge is not a very big part of the pattern. So it'll find enough of these edges, and it'll end up drawing this edge anywhere. Because it'll find, we're asking it to find only 70%. Our score threshold is set to 70%. So finding both of these lines is probably like 80%. It'll just draw this line arbitrarily anywhere, so I can't see it. But by setting this line as an emphasis area, we're saying you need to find 70% of the whole pattern and at least 70% of this line as well. That's the beauty of the emphasis area. That's with the blue. So now we got a good pattern. We find it. We'll go back. We'll reset it up as a tool offset now. And what we're going to do is we're going to use tool frame 1. Tool frame 1 is basically centered on the pole shoes of this magnet, kind of at the end of this magnet, just a Z value. So the origin, so it's the XY of the tool frame is 0, and the Z is like 285 or whatever, down to basically where the center of this bar is. And the Z is pointing up, which is parallel to the camera, parallel to the optical axis of the camera. So we're going to use UTOOL 1 for this example. So we snap and find. You can see here. So again, everything's relative to the tool frame. So our origin of our locator is like 278, which is about 300 millimeters from the center, which is right. Now I'm going to just, for no good reason at all, I'm just going to change the origin, just to illustrate how the positional information is always relative to the origin. Now we are using, we're using nominal positions and reference positions. So where the origin is doesn't really matter. It's arbitrary. If you change it, you need to reset your reference. But you can see here that it jumped about 20 millimeters as I move my origin from here to here. But where the origin is doesn't really matter when you're doing reference positions or offset motions. If you want to use found position for some stuff, which you do, which is a whole other topic, then where the origin is does matter. So that's it. We set our reference position. We're going to go ahead and save it. Now we're going to go ahead and update the vision process to the one we just created. And then we're going to go ahead and run it. And our offset's going to be 0 because we just set our reference. So now I'm using, when I go to set it down, I'm using the same motions with, again, we'll look at this program, you'll be able to see it better in a minute. But we're using the V offset to guide it. And of course, that's going to not have any effect because it's 0. And then I'm using a tool offset for the approach and retreat. So we're going to go ahead, put it down. And now now the magic happens. So now we're going to arbitrarily relocate it. Now the robot's going to come. So the robot's coming to the same position, but the part is different. So the part tool relationship is random now. And now we're going to go discover the end of that part, but I actually pulled it a little too far. So what happens is I can't find it. So in this case, it just crapped out because it didn't have any label 500. A couple of different things you could do. I mean, you could have a larger field of view, depending on the application, how far off the part's going to be. You could even do some kind of histogram and decide, oh, it's too far in the field of view, let me automatically move back. What I just do is I just go ahead and jog it back. You'll see in a second here, so wrong way, here we go. And then I just rerun the vision. So there we go, found it. So you can see here our offset's about 109 millimeters in the X direction, a little bit in Y, a little bit of rotation. So now we're going to go ahead and we're going to set it down where we want it to be. So we just discovered the end of that and used it. Now we'll try again. We'll push it back the other way. So before we had so this should be a negative value now because it's about 100 millimeters positively it was off. Now it's about 3 inches back the other way. So now we're going to offset so the robot's going to go a little further into the table. Again, getting the part where we want it to be. We'll just do one more. Okay, I'll tell you what, it works. Let's move on. We'll look at the TP program. So here's our TP program, really. So all of that, we only used 3 positions. We had a perch, so out of the way. Then we went ahead and we did our pick drop motion. We used a tool offset. There was just a 100 millimeters in Z in this PR21. Moved down, turned our magnet on, waited half a second, retreated up to the same, the same position as here. Moved directly to our view position, executed our run find, got our offset, and then move back, and we apply. So you can use a tool offset for approach and combine that with a V offset, a tool offset for positional information to adjust the robot position to get the part where you want it back to its nominal position. So we go back to our place position, move down, turn the magnet off, and move back up and back to our perch position. So 3 positions, 17 lines of code. You're doing an iRVision guided place process. Pretty basic. That's it. I hope you enjoyed it. I'll take some questions now. One question that I often get is, when should you use auto grid frame set versus versus robot generated grid cal? Basically, robot generated grid cal is very good for large fields of view. Actually, with our new 3D area sensor, the field of view of each camera is quite large, and so you pretty much have to use robot generated grid cal. But whenever you're calibrating a vision system, you want your calibration data to encompass the entire field of view. So you can imagine when you have a large field of view, getting a grid that's big enough. We don't sell grids, or we don't provide grids that are big enough, but using robot generated grid cal, you could calibrate the whole field of view, because the robot is going to move to the entire field of view and going to generate data for the entire field of view. Okay, so I have a question here about what email address do we send in order to get the presented Excel sheet. Also, could you email this presentation to me as well? Yeah, I think first of all, this whole webinar is being recorded, so you could rewatch the whole thing at some point in the future. Probably next week, it'll be up on our integrator website. As far as getting the spreadsheet, you could email me. My contact information will be presented at the end of the presentation. It's david.bruce at FANUC America, but you'll see that at the end. And another question that would come up in terms of the pixel error limit. Some people were asking previously about that. When is it too high? And basically, let me get out of here. Hang on one second. Pull this up. So I'll just go ahead and I'll navigate. We'll just look at that. I could talk about that for a few minutes. But basically, when you calibrate the vision system, it'll come up with a magnification of millimeters per pixel. So if I go ahead and I go to my calibration, create Sony Cal, for instance. So you can see here, so the magnification in this case was about 0.5 millimeter per pixel, and the mean error and the maximum error is represented in pixels. And where the error comes from is, as I've been saying all along, the calibration is a series of pixel values corresponding millimeter values, comes up with a transformation. The error comes from checking that transformation. So it takes all the data and plugs it into that new transformation and compares it against what it should be. So it knows these two should equal exactly 0, 0. It doesn't by a little bit, and that's where your error comes from. So that's how the error is. And then it goes through and it gives you a mean error and a maximum error. And typically you want your mean error to be less than 1. And your maximum error would probably be less than 5. I think you might be okay. When you get a fisheye type application using a 6 or a 4 millimeter lens, you get a lot of distortion around the edges. You're going to see a maximum error value. And by the way, like I did previously in my examples where I deleted some calibration points because the data were bad. Those were actual bad. Those weren't circled. If there's a circle, and you'll get out towards the edge of a fisheye type application where you'll see that the error is high there, but it's actually a circle. You want to leave that data in. You don't want to delete it. Leave that as part of the calibration. So that's basically 1 in 5 is a good rule of thumb for mean and max error. I think we were seeing it at 20, so I knew there was definitely something wrong. Okay, I have another question here. If your robot doesn't have iRVision option turned on, is there a free demo way to turn on the option for the robot grid calibration? can be done. Obviously, we already have the camera and cable. A good guy to talk to on that would be Scott Martin. He's on the hotline, and he deals a lot with integrators and stuff like that. I do think I remember seeing there was some sort of temporary iRVision way of loading it for 30 days or something. I seem to recall that. Of course, and if you work with your district manager as well, they may be able to help you get it set up temporarily. And we will certainly we'll email you Scott's information so he can get back to you directly. Back to my presentation here, sorry. So I think that's it. I would just little pull it down here. Try it. iRVision is easy to use. A lot of this stuff too, you can do. You can do a lot of this stuff right in RoboGuide, which is a whole other topic. But you can bring in virtual cameras, and you can set up, and you can bring in calibration grids from our iGIS library, and try a lot of this stuff in the virtual world, which is a great way to learn stuff. So I think that's it. I hope you enjoyed it. I hope you learned stuff. With that, I'm going to turn it back over to Robert.
Thank you, Dave. Very, very well done. I certainly learned a lot. I hope you all did as well. I'd like to remind you we do have some upcoming webinars in 2 weeks, same time, same place. We're going to be covering force sensing application basics with Virgil Wilson, and then 2 weeks after that, looking at version 8.3 of our core software application features with Glenn Nowak. I would like to please remind you to take our survey that's going to come up at the end of this webinar, as this helps guide our future topics and helps us improve these as we go along. Any questions that we didn't get to, or if you did ask a question and we told you we'd follow up, we certainly will. I'd also like to remind you that this webinar series is another one of the exclusive benefits of being part of our authorized integrator network. You can access a number of other helpful items, such as the FANUC Sales Toolbox, the Robotics Advantage program, one of our great marketing programs, many of our traditional marketing programs, and then also access to the CRC website, where you can take care of many of the common items that you normally deal with FANUC for. So this is Dave's contact information. You can contact him with any additional questions. He is here to help you and be successful in your particular applications. We hope you enjoyed yourselves. Have an excellent Friday and an excellent weekend, and we hope to see you next time. Thank you very much.